And also, real quick, sine and cosine. Range, outputs, y-axis. How far up and down does sine and cosine go if they haven't been shifted from -1 to 1? So it kind of lives within those bounds, right? And it just goes forever both directions. Are you guys with me? Tangent. Oh, good.
So the range would be -1 to 1 then.
Yes. I love it. And of course, if you change any amplitude or whatever, it changes, but the fundamental sine and cosine, -1 to 1. What's weird about tangent? What's the weirdest thing about tangent's graph? There could be a couple things, but there's something tangent has in it, in the graph, that sine and cosine don't have, that make things really weird. There are these asymptotes. So an unshifted tangent, if I ask you what the domain is, there's kind of a strange way you can write it, because here's the base tangent, correct? This is not good enough for a homework problem, but it's good enough for this discussion. Have I graphed the entire tangent function?
No.
Why not?
Keeps
going. I love it. So it goes forever in both directions, just repeating this, correct?
Yeah.
So what does the domain have to not include? For example, what I've drawn so far. So the domain can't include what? For example, what values do I have to throw out? -π/2, right? -π/2, π/2. That's all we know for right now. But of course, so that's for the base tangent function that we normally draw, the one cycle. It lives between -π/2 and π/2, correct?
Mm-hmm.
But if I want to talk about the entire tangent function, that's where things get weird. Yeah. So what would the next thing up be, for example? What would the next asymptote be? Because what's the period of tangent? Pi. So where would the next asymptote go? 3π/2. So it'd be π/2 to 3π/2, correct? You guys remember this symbol? I should put it up here, but or yeah. Let me stop for a minute. There's some interval notation kind of stuff happening. That's still not anywhere near everything, but it's one more thing, correct?
Yeah.
And of course, I can go backwards the same way. So what's a way that I could capture all of these things in a single go? Is that what you're getting at, Brandon?
Yeah.
Okay. Yes.
Should I answer?
Sure.
You could say that the domain is -infinity to infinity, but x cannot equal π/2.
Okay, so you can say domain infinity to infinity. That's a big ass comma. Excluding x equal to.
π/2 plus n pi.
Okay, good. π/2. And just to kind of, it's interesting because, especially if you use n is normally natural numbers. Can't it go forward and backward? Right? I went forward one, didn't I? Can I go backward some?
Yeah.
Right, not some, but an infinite amount.
So, yeah.
Plus or minus. And I'm not sure if the book uses this. I can't remember what the book uses, to be honest. But yeah, we'll use n for now. So for example, what does the second interval leave out? π/2 and 3π/2, correct? So what if I made n 1? What's π/2 plus pi?
3π/2.
Yeah, π/2 plus pi is 3π/2. What if I made n 0? π/2 plus 0 is π/2. So this is a good way to write this more succinctly, because it's really difficult to write and capture all these separate parts. Yes?
So instead of wording the word excluding, can you be like x cannot equal?
Sure. You can do this.
Gotcha.
Yep. And you can even say that in English, right? You just say excluding π/2, give or take some multiple of pi. Because again, how far apart will every asymptote be from the next asymptote? Pi, because the period of tangent is pi. So all I'm doing is saying, go up so many and go down so many and forever. And you're gonna hit all the asymptotes that you throw out, yeah.
If n equals 0.5 and you have
No. N specifically as a natural number. That's why I use the letter N. What are natural numbers?
1, 2, 3.
Yeah.
All numbers?
Positive.
This should be whole numbers, but N normally means natural numbers. But yeah, we include 0, so it could be whole numbers. So it doesn't include the possibility of decimals or fractions, right? Okay. Because you're right, if it could be anything, then that's basically everything. Okay, so that's a little bit strange, your question, but this is a good skill to recognize now, because when we start solving trigonometric equations, we're going to see this kind of thing popping up. So for example, real quick, we've already done a very simple trig equation. Sine of what is 1/2? Give me one answer.
Sine of 45 degrees.
Huh?
Sine of 45 degrees.
No, 45 degrees we add 2 over 2. I want it to be 1/2.
Pi over 6.
5 or 6, right? Sine doesn't like it when it's close to x, it likes it when it's close to y, so when it's going to be small, 30 degrees, pi over 6. So one answer is pi over 6. How many answers are there?
Multiple.
Infinite number. There's one more answer that lives between 0 and 2 pi. Where else is sine going to be positive 1/2?
7 pi over 6.
No, that would be negative.
5 pi over 6.
5 pi over 6, yeah. Can we stop for a minute? Is everybody cool with that? If I just said, and you've seen problems like this, what's x so that sine is 1/2, and they wanted you to live between 0 and 2 pi, that would be the two answers, yeah.
What if, why not the one below it for pi over 6? Not
'Cause that would make-
positive.
These are where sine would be negative, and that's not supposed to be negative.
Okay.
So it can only be up there. Now, if I don't force myself to live between these two, isn't another answer going to be 2 pi later? What about 2 pi before that one?
Yeah.
So I got to pick up all the coterminal shit. So how do I do it? Plus or minus 2n, well, let's do it this way. 2 pi n. Plus or minus 2 pi n. So that would be the answers just thinking about one rotation. That's where the sine is positive 1/2. Where the y piece of the triangle is 1/2. Is everybody with me? If it was negative 1/2, it would be these two answers. Below the 180, right? Okay, maybe. And then I could just add on the period times whatever amount, just to capture everything. So I'm not sure of the book, I'm used to using like a K instead of an N, because that's a little more general. That means like negatives and positives, and then sometimes you don't see the plus or minus, but I normally put plus or minus just to really make it in your face that you can go forward or backward, right? You can go rotate forward or rotate backward. Is everybody semi with me? This is still in our future. We're not really here yet, but I just want to show you one example where that idea is useful for us. How to write an infinite number of things in one quick way, yeah? Okay. So when you write this, you can tell somebody, you know, what'd you do this morning? I wrote an infinite number of things. What'd you do? Oh, sure. Okay. Or not, I don't know. Could just work for me and my fellow geeks. All right. Anything else from homework stuff or generally? Yes.
I was wondering if you could, for when graphing trig function, Brendan, what was the problem you said you, 21 for 4.4 is the
Yeah, 4.4.1.
I was wondering if you could explain because I remember you showed us how we could find that if we did.
You did the cosine? No?
It's
So that problem is the secant, right? Okay.
just spacing for each point.
So here, let's do that problem. That'll be a decent little review of all that business. Yeah, I don't think no, this will be really fun. It's been a crazy week, and you know, I didn't say there was a quiz today, did I?
No.
Okay, good. I was like, I could have, I can't remember. Okay. And then one thing, I didn't have time to watch my YouTube video. Sometimes that's one thing. If nobody watches YouTube video, it still helps me. I'm like, did I say there was a quiz? No. Okay. Okay. so what is it? It's 2 plus 3 secant
Yeah,
2x minus pi, okay.
yeah.
So we're gonna pretend like this is cosine, right? Okay. Can somebody tell me the amplitude?
3.
3. Can somebody tell me the new period?
Pi over 2.
Hmm?
Oh, sorry.
Hmm?
Pi. It's just pi.
What's the original period of cosine?
2 pi.
2 pi.
Yeah.
I'm gonna divide that by
2.
2. If it was tangent or cotangent, then it would have been pi over 2. Is that cool? It's whatever the original period was, divided by that multiplier. Because that 2x actually compresses in this direction. That's why I'm dividing by that, yes.
So for that problem, you wouldn't factor out the two?
I will. So now if I ask for the phase shift, what do I need to do?
Factor out this.
Oh, okay.
Yeah, for this one, I really don't have to do that because I can tell it's 2, right?
Yeah.
But when I take a 2 out, 2x divided by 2 is x, pi divided by 2 is, crazily enough, pi divided by 2. So what's the phase shift?
Right,
Pi over 2 to the right.
Yeah, right, pi over 2. So instead of starting at 0, I should start at positive pi over 2 now, right? So like, if I do my begin, and we saw last time, Jeff beautifully made a nice mistake to show you how important it is to do the beginning and end, especially when there's multiple things happening. If you're not careful applying them in the right order, you could end up in the very wrong place. But when does cosine start? It starts when the inside is 0, and it ends when the inside is 2 pi, yes?
Yeah.
So if I solve these, it starts at pi over 2, which we already knew, and it ends at 3 pi over 2, which makes sense because the period for this guy is supposed to be pi, correct? You guys all with me? I need you to see how, I don't know if this feels like a lot of work. This didn't take me very long, correct? And it shouldn't take you very long. But the beautiful thing is, you can kind of like check yourself. The new period is supposed to be pi, and sure enough, pi later it ends. That's what period means. From where it starts to where it ends should be pi, and those are pi apart, yes?
Yeah.
3 pi over 2 minus pi over 2 is 2 pi over 2 is pi. Sweet.
I wanted to, because in office hours you were showing me how I could find the points for the graphs by.
Yes, we're gonna do that next. The step size?
I don't remember if it was step size, because in my notes I put it as finding space between points.
Yes, step size, okay. So the step size is gonna be the period divided by 4, because I always break, there's 4 main places where it starts. First step is normally, for cosine, is normally where it goes to 0. Another step for where it's 0, I mean negative. Another step 0, another step, so there's 4 steps I take to get through the main anchor points for cosine or sine. Are you guys with me on that? I need you to understand, if I take 4 steps, and what do I mean by that? I start high. First step, I go to 0. Second step, I go to negative. Third step, I go to 0. Last step, I go back to high. 4 steps gets me through the whole cycle. So if I can figure out how far each cycle step is, I can graph this thing pretty easily. What's the only thing I haven't talked about from the shifting? What's the only thing I haven't done yet?
The vertical shift.
Yeah, the vertical shift. And that one I do at the end. Just graph everything and then I'm gonna take everything and just shift it up to you, right? Now you could, no, I don't. All right, so this amplitude is 3. I know I'm gonna shift up in a minute, so I'm gonna give a few more. I'm starting at, where am I starting?
5.
Pi over 2, right? My step size is pi over 4, so pretty. So for when you're doing this, this wasn't that horrible. Does everybody agree? And the funny thing is, all of this work makes the graph, it has to be easy. All of this work should make the graphing step easy. The one thing you should do for yourself is instead of putting pi over 2, I'm gonna put 2 pi over 4 so it matches with this, so then I can step easier. That's the one thing I'm gonna do to be nice to myself. So I'm gonna start at 2 pi over 4, so the first step takes me to,
3 pi over 4.
holy shit. The next step takes me to pi, 4 pi over 4, so the next step takes me to 5 pi over 4, and the next step takes me to,
3 pi over
yeah, 6 pi over 4, which is 3 pi over 2, which matches with where I was supposed to end. See, it's kind of nice. It's kind of nice to see your own work kind of matching with what the hell you're doing later. Yes?
Just one question. You just put 2 pi over 2 because it was reduced to pi over 2, right? For a beginning point.
Here?
Yeah.
Oh, yeah, I could put pi over 2. I just put 2 pi over 4 so I can add over 4 easy. Yeah, okay. All right. So cosine starts where?
At 1 over
Max
so
at the
you
highest,
start at
yeah.
3.
So it starts at the highest, then it goes
Just start at 5.
0.
0, then it goes,
Negative.
Lowest,
oh yeah, negative, and then it goes
0,
0, and then it goes
3.
highest.
the highest, 11. That's the power of doing all the step stuff. Then I can just throw in the major points. If it was sine, I would have started there.
Yeah.
And then got up, right? So, is this going to be the answer?
No.
So I'm not going to do a solid line. I'm going to do dot. So this is not the answer for 2 reasons.
Yeah.
I'm going to do a dotted line.
You still need to shift it up too.
Yeah, I can shift it up too. This is where I love my students who are very precise. I would not do this if I was a student in this class. If I was a student in this class, I would hate me. But, because I just look at how I write. But the students that use like color pencils, I'm always like, oh, a little tear. I'm like, oh, that's so beautiful. Because I would never do that. That's awesome. So I'm going to raise every point up 2. So that goes up 2, that goes up 2, that goes up 2. Yes,
Not pi?
sorry?
Would it not go, sorry, to 0?
No, it goes up 2, right? So it's a -3, so it goes with the -1.
There.
Yeah, every now and again. Up 2, and then up 2. And then here's where you can, oh, I should have done this already, shoot. This is where things get a little nifty. Let me see if you guys are cool with this. Does everybody agree there would have to be an asymptote here? Right, because it's gonna be an asymptote wherever it's 0, yes? Okay. Because I'm not graphing cosine, I'm graphing secant. Is that all right?
Yeah.
So now I've got this, and I've got this, and I've got this. Is that all right?
But would the vertical asymptote still work just by you shifting the?
Yeah, because before I did this, the secant of when cosine is 0, I'm gonna have an undefined, I'm gonna have a wall. Then I shift it up by 2. So that's why I should have put my walls first. If I shift this wall up by 2, isn't it still just an infinite wall?
Yeah.
Okay. So moving it up and down, the asymptote doesn't give a shit. It's just this infinite pole. I'm like, can you move it up? Sure, it's exactly the same.
Yeah.
Right? Because it's infinite. It doesn't care how much you move it up or down. Is that all right?
Yeah.
Okay, so that one was definitely strange because it had basically everything happening. Not only was it a secant, it was also shifted up. It had everything happening.
Yeah.
Okay, love you guys. Okay, all right. Okay.
I have a quick question
Yes.
for the phase shift. So, if it wasn't, the phase shift part is kind of confusing because so it's already what right?
Yeah. This step is the step that's kind of like extra. I didn't really need this step because I already knew it was going to start at pi over 2. This step just kind of confirms that. And then this step is nice to make sure that I got the period right. And then I end up in the right place when I do my step size. So I look at all this work. A lot of this work is redundant. But it's kind of nice because you can see it how it's checking and balancing. You're like, okay, I stopped here, I was supposed to stop there, oh good, right? So it's supposed to kind of help you make sure that everything's on track.
Okay.
Okay. Yes.
The phase shift was like.
Oh, sorry, so
Since we didn't answer my question last class, the question I have now, it would answer it. So the graph of negative cosecant and secant would relatively be about, they would look about the same,
No.
right? Or is it negative secant and then cosecant?
has everybody got what they want from this year?
Yeah.
More than you wanted? Okay. So, just to draw a really crazy rough ass sketch of secant. So I think about a cosine. So secant would go like this,
Yeah.
right? Okay. Cosecant would just be shifted over from that, because if I just move this over, I get the sine function, correct?
Yeah.
So if I do negative secant, that won't be the same as cosecant. It'll still be off by 90 degrees, by pi over 2. So if I just do negative secant, that would become this. Right?
Okay.
Whereas, this might be too much here, whereas cosecant would actually have this. They're still offset. Yes?
Okay.
Yeah, okay. Now, secant and cosecant, if you just stand really far back, they look exactly the same. Cosine and sine, they both go like this, yes?
Yeah.
They're just, which one is kind of shifted by so much from the other one. Same idea. If I just took sine and I did negative sine, is that equal to cosine? No, it's still offset. Right, is that okay? If I took sine and I flipped it, does that become cosine now? Is that cosine?
No.
No, okay. So the same thing should happen with secant and cosecant because they're built off of sine and cosine.
Okay, now, what about negative tangent and cotangent?
The nice thing, all right, tangent and cotangent are more different, less similar, because one goes this and the other one goes that, right? So sure, if I flip one of them, it's gonna look more like the other one, but they're still gonna be offset. Does that make sense? The asymptotes are still gonna be in different places.
So my question was, if you were to just look at a graph of either one of them, and you didn't have the equation, how would you
Oh, okay,
know?
so if somebody said, construct the equation for this, I could make it a tangent or I could make it a cotangent. My phase shift will just be different.
Okay.
Does that make sense? You could use either one. Both equations would work out to be the same thing if you simplified one of them.
Okay.
But you could use a different starting point.
But that's not the same for cosine and.
Totally the same for cosine and sine, of course. Right, so if I said, all right, what's the equation of this? But I want it to be based off of cosine. Right?
Cosine of x plus 1. Minus 1.
So this is the cosine if it's been shifted with,
Pi over 2.
Fine,
yeah, pi over 2 over, so it'd be x minus pi over 2, right? That's one way to do that.
Okay.
Does that make sense?
Yeah.
So if you know it's a sine or a cosine, you can use either one, whichever one is easier, right? If you know it's a cotangent or a tangent, you can use either one. If you know it's a secant or a cosine, you can use either one, whichever one's closer or whichever one's easier, and if you can't tell which easier, pick one. I can't remember in the book, where, have you hit those problems yet where they give you the graph and you have to figure out the equation? Is that what you're talking about? No, okay. I didn't think there was that yet.
Well,
I
there
don't
wasn't
think
in the
it's part of the
homework.
homework assignment. I don't think it's part of the homework assignment.
No.
Is that negative tangent?
Say what?
Is that negative tangent?
Yeah, this would be negative tangent. Yeah. Cool. Because it would be tangent just flipped. Yeah. Okay. And it looks like cotangent.
Yeah.
How you guys doing? You guys all right? Okay. Every question that just happened was a little further beyond what we're supposed to be able to do, so you're fine if you don't quite fully get it. Okay. Yes.
I have a question about the other thing with the phase shift. If you made it pi over 3, say, and then would the step size change so that it would accommodate?
All right. So real quick. What if? Jeez, it's never enough time.
Just 50 minutes.
Huh?
Just 50 minutes.
That's not enough time. Okay. So then, real quick, this will be the last thing, and then we'll get into some new stuff. What kind of function? Sine, cosine, doesn't matter?
Doesn't matter.
Okay. Sine, you're saying if you shift it by pi over 3?
Yeah. Like
So let's say it's this. Is that all right?
Yeah.
Okay. In fact, let's make it, I want them to
We'll
be
actually make it
different.
like
Yeah,
two.
okay. How's that? So the new period would be pi, is that cool?
Yeah.
And the step size would be pi over 4, is that cool? Cut the period in fours, right? I'm gonna start at pi over 3, and I'm gonna step by pi over 4, yes? So I'm gonna make this 4 pi over 12, and I'm gonna make this 3 pi over 12. So therefore, I can add, and I already have like denominators. So effectively, I'm gonna be nice to myself. The math is already mean, let me be nice to myself. So that's what I would automatically do is, whatever the beginning point is versus the step size, make them LCDs, and then start stepping. 7 pi over 12, blah, blah, blah. Does that make sense? That's what I've done every single time, is I try to make the step size and the beginning point have the same denominator. So then it's easy to add. Okay. Denominator. Okay.
Denominator.
Yeah, I gave you guys the practice, that's right. So like number, did I?
Yeah, you did.
Okay. Just showing off my amazing memory skills. Number 5, number 6, right? Those are basically these things here.
Yeah.
I'm never overly worried about shifting the whole thing up or down, so I'm not gonna give too many of those. Okay. Number 6 is sort of like what you're asking, Chad, with the negative tangent.
Okay.
Yeah.
I have a question on part B for number 2.
Sure. What's the area of, now of course, does everybody know what a dartboard, if I put this on a test, I would give you a picture of a dartboard, but you know, it looks like slices, right? So this is a very simple dartboard, so it's not got any real, it's just got these slices, yes? Each slice has a certain angle to it, correct? What's the formula for the area? And I keep saying slices, but we know they're especially called sectors, yes? I think here I call them segments. Yeah, so sectors. What's the area of a sector of a circle?
Theta r squared over 2.
Yeah, 1/2 r squared theta, or however you want to have it memorized. Right? What's got to be true about theta though?
And radius.
It's got to be in radians. So whenever theta is in the wild, it's not inside of the trig function. So real quick, I can't remember. You got to forgive me. I'm pretty sure I did this with you guys. If I said, what's the cosine of a right angle? That's not an L. That's a right angle. Yeah. What's the cosine of a right angle? What's the cosine of 90? Cosine likes what? X. 90 degrees, is there any X? No. Is that an angle measure? That's a picture, yes?
Yeah.
That's a freaking picture. So if it's inside a trig function, I don't give a shit how you could talk about degrees, you could talk about radians, you can make a picture, you can call an angle Fred and say, what's the sine of Fred? I don't care. But if the angle is out in the wild, it must be something that has a real physical measurement. It's out in the wild now. It's got to be radians. It has to be radians because that's the only one that's a real physical measurement. I can't let it be degrees, because degrees are shit we made up. Radians are based on the radius of a circle is a real physical measurement. Are you guys with me? I think I made a big enough point about radians. Okay. Kind of hammer that home. Okay. All right. So, what I want to try to do today, it's going to be exciting. I'm going to do, let's see, almost like I'm trying to make you guys hate me. I'm going to do section 5.3. We're going to do some examples, 5.3, 5.2, and then we're going to call it a day. 5.3 is going to be a lot, though, so,
So we're not gonna go over 5.4?
We are also going to do 5.4. I didn't want to say that till later. Because 5.3, what's really funny to me about this book, they could have made 5.3, 5.4 one section, because you get them both at the same time. If I prove to you one thing, the other thing happens at the same time. Okay, but I didn't want to, like, really overwhelm. So we're going to start with the side that has this weird frickin' triangular conglomeration, right?
Have we done 5.2 yet?
That's the part we're going to come back and do after we do this.
Oh.
You'll see one. There's a reason.
There's a method to doing this?
Sometimes. Sometimes it really is just madness.
Thank you.
Now, I honestly do not know the way the book proves this.
Yeah.
And I'm pretty sure it proves it a different way. And if it proves it a different way, that sucks. Everything we're about to do related to this piece of paper, you are never going to have to do yourself. Does everybody understand? Every time, whatever math course, when I'm deriving a formula or something, I have to remind people, we're still in the derivation phase. None of this is something you're going to have to do yourself. We're going to do it together so that everybody sees where the formula comes from. We didn't just pull it out of our ass. We didn't just make it up. It actually comes from somewhere physical. Some stuff we pulled out of our ass, but not this stuff. All right, so I have the same thing you do. Except I think mine says something kind of weird, but it's all right. I think I deleted it up for you guys. So this is the same thing I use in my pre-calculus class, because they have a trig section in that class. So don't worry about this part. That's from their book. Yes, we know it's HEM. Okay. All right. So what I'm trying to do. Oh, yes.
Can we assume the shapes to the right are right angles?
Oh yeah. So how many right angles does it look like there are here?
3.
Yeah. So this one. So I'm going to go ahead and put in the right angle so you know for sure.
4.
There's one here. There's also one here, correct? There's one here. And then there's one here. So there's 1, 2, 3, 4. Yes?
Oh.
2 of them have this.
Oh.
1, 2. And then there's the one with that one, and there's the one with that one. Okay, you guys with me? So what this is for, and again, if you just want to sit there and watch, that's fine. If you want to try to capture what I'm doing, that's a little better, but you can just watch if you want to. What I'm trying to figure out is, what is the sine of one angle plus another angle? So just to be difficult, I wanted to throw some Greek letters at us, because you're going to see Greek letters every now and again in the homework. These are the Greek letters. Does anyone know what these are?
Alpha and beta.
Alpha and beta. I love it. Okay.
So you're finding the sign of alpha and beta?
I'm trying to figure out the sine. For example, one thing I want to know is, what's the sine of alpha plus beta? The other thing I want to know is, what's the cosine of alpha plus also the minus, so we'll get there. So let's see what we can figure out from this stuff here. This is 1. So ready with me so far? So this side is 1. So let's start with this big ass triangle here. Let me see, what's the best place to start? Yeah. Oh, okay, let's do this. This might be the best place to start. This triangle right here, this triangle that's at a slant. You guys all with me? Okay. How long is this side of that triangle? How long is this side? What angle is in it? What angle is in this triangle here?
Beta.
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 Which trig function likes x?
Cosine.
Cosine. So the cosine of beta would be x over 1, correct? It would be the x side divided by the hypotenuse. So this side is actually just cosine beta. This side here is just cosine beta. How are we doing so far? The funny thing is, yeah, if the hypotenuse is 1, this is sine of the angle, and this is cosine of the angle. Yes?
If the hypotenuse was like 2, would it be cosine?
Then it would be twice.
Cosine
Yeah, so
beta.
all I'm doing here is, what's the cosine of beta? Well, it's going to be the x side over the hypotenuse, correct?
Mhm.
So it'll be the x side over 1.
Okay.
So then what's x? Cosine beta.
Okay.
So when the hypotenuse is 1, the side lengths are easy. They're just the cosine and the sine. So this is not true, but it's a neat way to think about it. I think of the cosine as being the percentage of the hypotenuse that's in the x direction. And the sine, so what's this here? What's this side?
Sine of beta.
Sine beta, the same way, yes? Because sine beta would be the y piece divided by the hypotenuse, so it'll be y over 1, so what's y? Sine beta. Do you see the whole point of this problem? Yep. We're going to try to identify as many lengths in here as we can and just step back and say, what the hell have we done? Okay. All right. So what about, now let's look at this big ass triangle here. It's pretty cool. I'm going to call this big ass triangle. This is tilty triangle. This is big ass triangle. Okay. Big ass triangle. What angle is in its base?
Alpha plus beta.
Alpha plus beta, or A plus beta. Alpha plus beta. So can anyone tell me, for this big ass triangle, how long is this side here?
Cosine of alpha plus beta.
Yeah, cosine of alpha plus beta. Because again, its hypotenuse is 1, correct? So it's the same exact idea. X is going to equal, so cosine of alpha plus beta is going to equal x over 1, so x is cosine alpha plus beta. So that is this length here. Be very careful. Is that all right? All right, let me stop for a minute. Okay, now things get really nifty. Now things get nifty, yes. So for this triangle here, this triangle right here, what is its hypotenuse?
Cosine beta.
Cosine beta, yes? All right, this is where things are going to get weird. Everything was nice before because the hypotenuse was 1 for the triangles I was looking at, so that's why I did them first. Now I've got this, and again, it's okay. Just sit there and absorb or try to write. You're fine. This hypotenuse is cosine beta, correct?
Yeah.
So for example, this side here, what's the angle in this triangle here?
Alpha.
Alpha. I like it. So, you would, Jeff. Let me see if I can do this here. Yes. Looking at that triangle right here, right? What would the y side be? Well, what would sine of alpha be?
The y side. Oh, it would be.
In fact, and again, don't let any of this shit trip you up. You know what sine is. What sine? What side over what side?
Y over r.
Y over that hypotenuse, yes?
Yeah.
So it'll be y over
Cosine.
cosine beta. So then what's y? Multiply this sucker up, right? Sine alpha cosine beta. So all I did you guys were all cool with this being cosine beta, correct? This is cosine beta all the way over, yes? You guys were all cool with that. But now that is the hypotenuse of this poor little squat dude, right? Squat because he's been pushed in. So therefore, when I try to figure out this side, when I use sine, it's going to be over this. It's going to be over cosine beta. Before it was all fun and games because it was over 1. Now we're over cosine beta. So this side is now sine alpha cosine beta. This is fun, Jeff. Okay. Can we do this every day? No, sorry. I guess it was fun.
Can you push it up a bit?
Yeah.
No, the other thing.
What happened?
The
I can't do much
sine-
more than this. Huh?
No, the sine.
Oh, this one. Sorry.
Yeah, yeah. There you go.
So that was just sine of alpha would equal the y side over the hypotenuse, correct? Yes.
Does that say 1 over sine of alpha times cosine of beta?
1 over what? Sorry? Oh, no, this is the y. Sorry, this is the
Oh.
y. So we figure out the y was sine alpha cosine beta.
Thanks, I'm good.
You're welcome. So therefore, what about, this sucks. What about this side? So that would be the x piece of this whole thing. At some point you guys are going to give up on trying to keep track of this, I understand, but just, that's why I said you can watch if you want to. So if I did cosine alpha, what would that be? Again, don't worry too much about the details. Cosine is always what side over what
Y
side.
over cosine beta? I mean x over cosine?
Yeah, it'll be the x side divided by the hypotenuse, correct?
Yeah.
Whatever the hell those things are. So it'll be the x side divided by the hypotenuse. So then won't the x side be cosine alpha, cosine beta?
Mm.
That's what this whole thing is here. Let me take this out here. Okay. Oh, this is exciting, Jeff. Okay.
This is torture, Jeff.
You're welcome. You're so welcome.
My eyes burn.
Now, let me see if you guys, alright, let's see how you feel about this. Alright. If I draw a line here, didn't I just make another little right triangle here? Okay. I'm gonna watch you guys. Every now and then I'm gonna see one more person put the pencil down. Is that cool? I have to make right, I'm sorry, you didn't even see what I was doing. If I draw a line here, I made another little right triangle here, correct? You're all like, yes, Jeff, good job.
Sure.
Just to cut to the chase, if I wanted to figure out what that angle was there, I could kind of work with the angles that I know. Eventually, I would get that this angle is alpha. That angle right there, yeah.
But did we just make another itty bitty triangle right under that?
Huh? Oh, right there? Don't worry about him. He's okay. Stay with me. Don't try to see where I'm going with this. I'm sorry. You really can't. I'm really sorry. For the moment, we're just working with little triangles. We know every damn thing about every right triangle ever. We got Pythagorean and we got trig. If I give you a right triangle, you can just tack the shit out of it, yes? So here's a bunch of right triangles. And what are we doing? We're tapping the shit out of them. Okay. Why are we doing that? Because I want you to. Now, look at this same triangle right here. What's its hypotenuse?
Sine over beta.
Sine beta, right? So what would this side be? This is the x side, right? So if I do cosine alpha, what would that equal? X
X
over
sine
sine
beta.
beta. So this side will be cosine alpha sine beta. That's this side. Don't worry, I have a cleaner thing I'm going to replace this with in a minute. Because this is getting crazy, right? I agree. So let me see if I can cut to the chase. That's cosine alpha sine beta. So this side is going to be cosine alpha, cosine beta. No, I'm sorry, the other way. Sine alpha, sine beta. Yeah, so this one's the y side. So this is going to be sine alpha, sine beta. I think I'm ready. Yes. Okay. There's one side I didn't put down here, but let me show you. So let me go to the cleaner one. Here we go. You ready? You're going to be able to see this better. So there's everything we've done so far, except for one thing I forgot, which is this guy. But this guy's pretty easy because it's just the y side of the big ass triangle where the hypotenuse was 1. So it's just sine of alpha plus beta?
Yeah.
Okay. Oh yeah. Did I leave out? I think I left out something. You're fine, Jeff. Oh, I did. I sort of like, okay, that's right. Okay. Let me stop for a minute. So here's the important part. Even if you didn't follow every single detail, do you guys see how every single thing I did was basic trig? If I know the hypotenuse and I know another side, I could figure out, I can use a trig function to figure out whatever sides I want to, right? You guys all with me? That's every single step I did. They got weird quickly because the hypotenuses got weird quickly. This hypotenuse was a piece of this one. So of course when I went to this triangle, its hypotenuse is weird, so its parts get weird. But look at what this says now. Look here. What's the sine of alpha plus beta? What must that equal? This plus that, yes? Because that length would be the same as that length. So I know now sine of alpha plus beta equals sine alpha cosine beta plus sine beta cosine alpha. That's an identity that you must memorize. And I will give you a way to memorize it based off of the other guy. Now watch this. Cosine alpha plus beta is equal to this minus this. You guys see that? Cosine alpha plus beta is equal to this minus this piece. So cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. Okay, you guys are all appropriately excited. So I could have just told you this is true, but I never can do that. And again, if you didn't understand every single step I did, you at least can see you could do this. You really had to. It's built off of basic trig. It just gets to the point where it looks gross. But I didn't do anything that was more than just cosine of an angle is x over that hypotenuse. That's all I did, every single step. It's just that, sorry? Yeah. It's just that as I progressed, my sides got worse and worse, but still, every time I set up a ratio for cosine, it was x divided by hypotenuse. Sine, y divided by hypotenuse, okay. Now let me see if you guys remember, so let me do this. Let me write this let me take the alpha beta away for a minute, because maybe that's kind of getting us down, yes?
How did you find the small part where we subtracted sine alpha? Sine
This guy?
Oh, okay.
Yeah, I'm sorry, yeah. It's the same length as this here, right?
Yeah.
So this plus this equals this, so therefore this equals this minus that. Yeah. So let me see if this helps out. What if I write it like this? Sine of A plus B equals sine A cosine B plus sine B cosine A. Is that better with not Greek letters? I don't know. Cosine of A plus B equals cosine A cosine B minus sine A sine B. Now, what would sine of A minus B be? Watch this, you ready? So it'd be sine A cosine of negative B. Is that all right? Don't I have a negative B there now?
Yeah.
I know in general how to do this, so whatever this is, I put it there. So whatever this is, I put it there. Plus sine of negative b cosine a. Who remembers their identities for putting negative angles in? What is cosine in negative b?
Still positive.
Yeah, still cosine b. What's sine of negative b? Negative.
Sign.
Negative sign
Okay. So sine of a minus b. So just to cut to the chase, I can do the exact same thing with the cosine. And I'm going to end up with cosine a cosine b plus sine a sine b.
Quick question.
Yes.
Are all of these identities or just the first two?
So these two. And if you notice, now here's what's interesting. You really only have to memorize two things.
Yeah.
So here's your first example of something very strange. I've gotten a few of my colleagues to teach it this way. Cosine is an asshole. Look at sine. Sine of a plus b. So what does sine say? Hey cosine, let's take turns. I'll do sine a, you do cosine b. It's a plus, I'll keep it a plus. And then I'll do the b and you do the a. You guys with me? Sine's nice. Yeah, let's take turns, cosine. I don't know if you guys are with me at all. I'm trying to give you a way to remember this. So sine is nice. It says, I'll take a turn with A and you get B, I'll keep it plus, and then I'll take B and you take A. We'll take turns, right? Cosine's like, all right, sounds good. Cosine comes along and says, me first, cosine. You got a plus, screw you. I'm going to make it a minus, and then you get shit at the end side. I don't know. I don't care if you think it's weird. It's just the way I remember it. And the funny thing is, this is the first place I realized cosine is an asshole kind of makes sense. And then as I taught further math, cosine remains an asshole through calculus 2. It's just this idea that cosine is an asshole just kind of goes. Yeah.
I kind of remember it how it is in like a sequence of like sine, cos, sine, sine.
Yes.
And then you can just add the variables as you want it. Because it'll always be, like you said, it'll be A, B, B, A, and A, B.
Yeah. Yeah, whatever. If you don't like my cosine is an asshole, if you don't like that. Number one, if it's because you don't like to cuss, then you can say cosine is a jerk. Number two, if you don't like the idea at all, just come up with a different way to remember. But the way I think about it, I don't have to remember 4 things. Just have to remember 2. If it's a plus in the middle, sine stays positive, cosine stays negative. If it's a minus in the middle, sine stays negative, cosine makes it positive. Do you see that? Yes.
So, it would be safe to say that sine likes y, but it's kind of liberal about the x-axis, whereas cosine absolutely hates the y-axis with a passion.
Okay. Yeah, okay. Yeah, sure. I love it. Yeah, that'll work. I appreciate that. You're trying to improve upon I always appreciate that.
Cosine slept with sine.
Let's do sorry?
Cosine slept with sine.
Oh shit, alright. Yeah. Yeah, you can add on to the lore. I'll determine if it's canon or not, but you can add on to the lore. Okay, let's do a concrete example. You guys want to do a concrete example?
Okay.
Or no, you want some more theory?
Wait, sorry, can you go back?
Sure. Wait. I turned everything around. Here.
Okay, got it.
Alright, so watch. Before today, there was no way we could do this by hand. And you're all like, I was okay with that, Jeff. We're going to do this by hand, and then we're going to check our answer with the calculator. So don't touch your calculator right now. Can you rewrite 75 degrees as either the difference or the sum of 2 angles we know stuff about? What do we know about? What angles do we know stuff about? 0, 30, 45, 60. So can you take 2 of those and combine them and make 75?
Yeah.
Yes.
30 plus 45.
30
Yes.
plus 45, yes. All right, what's sine of a plus b? What's sine of 30 plus 45? What's sine? Sine's the nice guy.
Sine of 30.
Yeah, it says, let's take turns,
Sine.
cosine.
45.
That's a plus, so I'm going to keep it a plus. Sine's the nice guy.
Yeah.
We'll take turns. I'll keep the sign the same. Now I'll take the 45 and you take the 30. You guys still with me?
Mm.
That's a concrete example of using this. Now we know all this shit. What's sine of 30 degrees? We should know
1/2.
1/2, good. What's cosine of 45?
Rad 2 over 2.
Rad 2 over 2. Sine of 45, of course, same thing. Cosine of 30?
Rad 3 over 2.
So you get rad 2 over 4, is that cool?
Yeah.
Plus, what's rad 2 times rad 3?
Rad 6.
Yes, half of 2 times half of 3 is half of 6 over
4.
4. I always get people that suddenly forget you gotta multiply and whatever, right? That is the exact answer for sine of 75 degrees. Can somebody plug this in your calculator? You guys understand now when I said earlier there's not enough time?
Yeah.
Okay. So if I do square root of 2, make sure you're outside of the square root before you keep going, right? Divided by 4 plus square root of 6, get out of the square root, divided by 4. Is that cool? Oh no, wasn't that good? Look at my poor little calculator. About to die. I get this. Is that cool?
Yeah.
Now I'm gonna double check, make sure that I am in, oh shit, I gotta be in degrees, right? So now I'm just gonna do cosine, what was it, sine? Sine of 75. Same damn thing. Go humans. Right? You get the same damn answer the calculator did. Go us. Okay, maybe. No, screw it. So, just to make things a little more interesting, what if the question had been, what is the cosine of pi over 12? Don't make that degrees. What radians do we know? So 30, 45, 60, 90, 0, all that's great. What about radians? We know
Pi over
5
4
over
and
6.
pi
pi over
over
4, pi over 6,
5 over 3.
pi over 3, 0, pi over 2, right? That's all we gotta know. We only ever have to know the first quadrant because the other ones are just slapping negatives on sometimes, right? So ready with me? Can I rewrite this in terms, in fact, 12 would factor to be, in terms of stuff we know, 3 and 4, correct?
Yeah.
So this is probably the difference of two things that are based on 3 and 4. See if you guys are cool with this. So, for example, if I just start playing with this, isn't cosine of pi over 12, isn't that equal to 4 pi over 12 minus 3 pi over 12? Yes? And what's 4 pi over 12?
1.
Reduce it.
Pi over 3.
Pi over 3.
Pi
And what's 3 pi over 12?
Pi over 4.
Pi over 4. Okay. And that's the shit we know stuff about. So how does cosine work? Cosine of the difference here. Cosine's an asshole, so he's like, me.
Cosine.
I'll do both. There's a minus sign. So cosine says, I'm going to make it damn plush. And then it says, yeah, you go for it, sine, whatever. I can sense how much you love this, okay. So what's the cosine of pi over 3?
1/2.
Yeah, because that's far away from where cosine likes to be, so it's going to be the smaller option. Cosine of pi over 4, of course, is
Rad 2 over 2.
rad 2 over 2. Sine of pi over 3 is
Rad 3 over 2.
rad 3 over 2. Sine of pi over 4.
Rad 2. Wait, it's the same as
Yeah, I know, it's nifty. You get rad 2 over 4 plus rad 6 over 4, which is the same as what we got, correct? And you'll see why in a minute. Isn't that the same exact answer we got before? And sure enough, if I do, and let me change to radians. So if I do sine, what's the sine? No, cosine of pi divided by 12, I get the same damn answer. Real quick, why is that not surprising? What is pi over 12 radians in degrees?
15.
It'd be 180 divided by 12, 15. And what's 15 plus 75? 90. And remember how sine and cosine are equal to each other as long as their angles add up to be 90? So that was a whole extra thing. It doesn't matter. It's not. It just was a little side note. Oh, this is why they're the same. Okay. I guess. Alright. So there will be some problems like this, or with degrees, where you could either make it into an addition or subtraction problem based on angles we know. And then you can get the exact answer, right? Look on the other side of this beautiful handout I gave you. Shice up. Where did I put them? There. Alright, so here's what we're going to do for the rest of the class here. This is section 5.2, but it's also in 5.3 and 5.4, right? This is the idea of verifying identities. So, when I have to verify an identity, real quick, when I'm solving an equation, don't I do stuff to both sides? The only time I'm allowed to do stuff to both sides is if I know or I'm assuming that they are equal. That's a property of equality. When I can add, subtract, multiply, divide, both sides by the same thing, it only works if they are equal. I don't know if they're equal. I have to verify that they're equal. You are never allowed to do stuff to both sides if you don't know it's truly equal. So you can't, for example, multiply both sides by sine. Do you see why you would want to do that? So I could kill the fraction? A 2 bad. Right? You cannot do that. This is something that is glossed over in algebra. But every equation you ever solve, you are assuming the equality is true, which is why you are allowed to do shit to both sides. Here, it's saying expressly, I don't know.
So you can't assume.
Can't assume. I cannot do stuff to both sides. I will tell you this, when they say verify the identity, they're kind of saying it is true, so you know it should work, but you're not allowed to do stuff to both sides because you're verifying that it's true.
So you can't take the square root either?
No, because that would be doing something to both sides. I cannot do something to both sides. I can work with each side separately. So how do I verify this? If I can make one side look like the other side, I verified it. So do you see anything popping out at you? So one thing you look for are basic identities.
The top.
Anytime I see a trig function squared, and like what I see here, I think Pythagorean identity. I am not saying every time you see a square it will be Pythagorean, but most of the time it will. Does anyone know what 1 minus cosine squared x is?
Sine x squared.
Sine squared x. By the way, I never said this, but are you guys all cool with the this is so weird. It's kind of like saying the word tree, not realizing everybody in the world doesn't know what a tree is. But when I write cosine squared x, that really is cosine x all squared. It's just a shortcut way to write. I never really directly said that, and that's my mistake, because I'm so freaking used to writing this, I don't even think about it. But we just, instead of writing freaking parentheses every time, we just decided to put the square there. But these mean the exact same thing. Are you guys with, yes? Sorry.
It doesn't mean though that it's just cosine x squared, right? That's wrong.
Yeah, it's not the same thing as cosine x squared. This is something very, very different. That says square the inside, then take the cosine. This says take the cosine, then square it. Is everybody with me? Sort of like this old thing about what's different about these two things. Remember this? This is positive 4, this is negative 4, right? That's 4. So it's negative 4, that's positive 4, okay. So let's look at this. What is 1 minus cosine squared x?
Sine squared x.
Sine squared x. And what's sine squared x divided by sine x? Sine x. I love it, because I just cancel one side. Is that all right? So I made this side look like this. Is there anything I can do to this side?
Expand tan.
Ooh, I like that. Kind of like rhymes. So expand the tan. So if I expand tan, what's it become?
Sine over cosine.
And what do the cosines do? Did I make these look the same? So here's how you do an answer for me for an identity. You do this. Check! Don't actually say check in the middle of the test. That's bad. But you guys with me? That's all you got to do is like say, there, I did it, Jeff. Leave me alone. Right?
So, can you just like say check, like, not say it, but like write check, and then that would be.
That's it.
Okay.
Because the point of this problem is, can you make one side look like the other side? Sometimes you will have to work with both sides. Sometimes you can just work with one side and make it look like the other side. Yes?
Can we just end it off with saying sine of x equals sine of x?
Do you understand how that's not good enough? I mean, sure, sine x equals sine x. But, so the point is that you've made one side look like the other side, therefore the original thing is true. That's the point. I'm not trying to prove that sine x equals sine x, right? Yes?
If this was on a test, and let's say we like didn't finish it, or you'd be like, it's not good enough, do it more.
Didn't finish it, how do you mean?
Finish it, it's not enough.
What do you mean, I'm sorry?
Like you just said, if we just put sine x equals sine x, you said it wouldn't be enough.
I'd probably just put a note. I don't know what kind of tone the note would have. But if I'm a student, I'm like, well, you're not taking points off. But still, sometimes I put a note like, you gotta show me what's important. If you just say sine x equals sine x, that's not telling me you understand what's important about what you just did. You're just writing what you got. I need you to show me something. Oh, this is what I did. I don't know if that makes any sense. All right, now watch this. What do you guys think? Is this looking nice?
No.
Holy shit. It looks gross as hell. Now, do you all agree with me that there is one side that I can definitely do more to? I can do more to one of the sides. I have stuff I can do to one of the sides.
The left side, because you could do like.
Yeah, the left side. It's got two fractions, correct? Now watch this. I need you to understand. The whole point of these problems is to make one side look like the other side. Does the right side have a fraction? Does the right side have more than one term? No. So therefore, that's telling me I want to combine the fractions on the left side. That's the only way in hell it could ever look like the right side. So basically, anytime you see fractions in one of these problems, more than likely you're going to want to combine them. And what's the only way you can combine fractions? They have to have like terms, like denominators. Okay. All right, you got it? Okay. So the way I look at fractions is, I got two fractions. What is this guy missing that this guy's got? This is where you got to be really careful. Somebody tell me. All right, you ready? You ready? I'm going to say something really weird. Neither one of these has a secant x on the bottom. Neither one of them has a secant x on the bottom. Neither one of them. So real quick, if I had a 1/8, if I had a 1/8, do you all agree there's a 4 in there? There's a 4 in the 8, yes?
Yeah.
Is there a 5 in the 8?
No.
No, good, see? Is there a 5 down there? No. There's a 4, there's a 2, there's an 8. You guys with me? There's no freaking 5, even though this is 5 plus 3. Who gives a shit? Because the whole thing about denominators and making like denominators is multiplication, division kind of stuff, yeah? So let me ask you again. Does this have a secant x in it? No. It's got a secant x minus 1. So this has a secant x minus 1. This has a secant x plus 1. What is this guy missing that this guy has? The whole freaking thing. It's missing a secant x plus 1. So if I had to do 1/4 plus 1/5, what is this guy missing that this guy has? Would you just add 1 to the top and bottom? Are you allowed to do that shit? No. So of course he's not missing a plus 1. They're actually missing each other. There it is. Right? So you give this guy a 5, you give this guy a 4, now they're all like, oh, they can be together. Okay. So I'm going to have to give this guy a secant x plus 1, top and bottom. And then I'm going to have to give this guy a secant x minus 1, top and bottom. So I gave this first guy this, and I give the second guy this. So now, do they have the same denominator? Yes. So here's where you gotta be careful. Is everybody semi with me? I mean, this, yes?
So why would you put secant x plus 1 on top of the one on the left and then secant
No,
x
it's
minus-
not. So real quick, do you agree with me that if I needed to give this guy a 5, I gotta do it to the top and bottom to be legal, correct? And why do I need a 5 here? Because he's got a 5.
Right.
So to make them have the same stuff, I give them each what the other guy has.
Oh.
So here, I have to give this guy a secant x plus 1. The only way to do it legally is top and bottom.
Oh.
That's all.
Okay.
So,
Now I get it.
very quickly, variables are numbers. Variable expressions are numbers. They will act the same way numbers do. So if I multiply top and bottom of a fraction by a number, I multiply the top and bottom of a fraction by the same variable expression. Because they're just freaking numbers, right? What do I get on the, so let me show you on the top, you gotta be careful because I'm subtracting this whole thing, yes? So that's what you get on the top. And what do you get when you multiply the bottom out?
Secant x squared.
Yeah, secant squared
Secant
x.
squared x.
Minus secant plus secant, so the middle term cancels. Minus 1. Does anyone know what secant squared x minus 1 is?
Tangent squared.
So again, remember, when you see a trig function squared, you think, let me check my Pythagorean identities, right?
Yeah.
Okay. So when you're doing these problems for homework, if you don't have a list of all your identities sitting next to you, I don't understand you. You desperately want them, so as you do the problems, you're like, oh, okay, that one will work here, that one will work here, that one will work here. Okay. So now I can replace the bottom. What happens on the top, by the way? Secant x minus secant x. 1 minus negative 1. 1 minus negative 1.
0
2.
plus 1. 2.
Yeah, I'm not subtracting 1, I'm subtracting negative. 1 minus negative 1 is 1 plus 1 is 2. And secant squared x minus 1 is tangent squared, right?
Tangent.
You guys with me? And then what's 1 over tangent squared? What's 1 over tangent?
Cotangent.
Cotangent. Did we make this side look like that side?
Yeah.
We took this side and we made it look like, weehaw, check. That seems really silly, I know, but this tells me you understand that you just did the problem. If you just write sine x equals sine x, I don't know if you understand what the hell you just did. And that's what I need to know. I need to know you know what the hell you just did. What have you done?
Let's go back down.
Sure. So any identity problem, it's going to be blurry for a second, sorry. Oh, look at it. Oh, thank you. Any identity problem, you're trying to make one side look like the other side. Sometimes you only have to work on the one side. Right, this side, this one I didn't touch the side at all. I just made this one side look like it. Sometimes you have to work with both sides. But as long as you can make them match, you're golden. Okay. Oh, you guys like this a lot. And again, this is a really good example of picking the wrong identity and then just being cool with it. All right, that didn't work. Let me try something else. Not a big deal. It's part of the process, is identifying the wrong way to go, right?
Like a process of elimination, if you will.
Yes. So real quick, what do you guys think about sine 2x? What time is it? Oh shit. Let me show you one thing about sine 2x. Isn't sine 2x equal to sine x plus x?
Yeah.
All right, what's sine a plus b?
Sine A times cosine B.
Plus.
Sine b cosine a. And what's sine x cosine x plus sine x cosine x? Sine x cosine x plus sine x cosine x is 2 sine x cosine x. So that is its own little identity, but it's built off of the one that we knew already. You guys see that? The identity for this is built off of the one we already knew. Remember. So to be fair, we're basically out of time, I'm sorry. So we'll finish this up next time and then we'll open it up to review. You got the practice test. To be kind, I'm trying this semester to be kind. Feels weird. You guys are like, you need to try harder. Alright. I'm only gonna make up through 5-3 do. You with me?
Next week?
Okay.
Yes. 5-4, you should try to do a few.
That's a good
This is the one. 5-3 is the cosine of a plus b, and for some reason they had a whole other section for the sine of a plus b. Are you with me? Okay, so on the test, I'll try to. I'm not sure what I'll do. But just to be nice on the homework, I think I'm gonna make through 5-3 do. You should try to do some of 5-4, but I'm not gonna make it do. Does that make sense? Just to help you keep up with the homework. Yeah.
Should make 5-4, try to.
No, I'm not gonna do it. Good try though. Yes.
So, for the video that's going up on YouTube, can you do like time signatures or whatnot for the, for timestamps for the YouTube video?
Holy shit, no.
Okay,
I am just happy I put descriptions.
okay.
If you want more than that, just be happy. You should be happy you're getting descriptions. I ain't doing more with it. Sometimes I get an email, like a YouTube message from somebody who's not in my class, and they'll say, I can't, can you do this? No, I can't do shit for you. No, you don't give a shit about you. Go watch Khan Academy, leave me alone. Yeah. I said literally that to somebody.
How much would you use of like cosine as an asshole?
Huh? It would help, which, you know, is a little too kind. I lean more towards cosine, so just, you have to remember cosine's an asshole. Yeah. If you want to, you don't have to use that.